Okay, we're going to take a look at matrix transformations. It's basically an extension of functions of real numbers in a sense, but where inputs and outputs are going to be vector, single row or column matrices. So we've been dealing with solutions to systems of linear equations, and we express the solution as an n tuple, right? Ordered pair, ordered triple, or ordered four tuple, five tuple, and so on. Right? The set of all n tuples is what we call n space, and we denote n space with this capital R with a superscript of n. And these elements, these things, we are going to call vectors. Okay, we've already kind of talked about vectors already. So the set of all ordered triples, where n is 3, right? That would be 3 space. They would construct 3 space. 2 space is the set of all ordered pairs. 4 space, the set of all 4 tuples. 5 space, the set of all 5 tuples, and so on. So here's the comma delimited form for a vector in n space, and the column vector and row vector form that we're familiar with. So all 3 of these we've already been using. So it's kind of just getting in, reiterating that idea. So we'll interchange the notation for vectors between these 3 as needed. Obviously, these last 2 will be useful when we're talking about matrix arithmetic, like matrix multiplication. Okay. In n space, we have something called the standard basis, and we're going to talk about basis later on in the course. This is the standard basis for n space. There's n vectors. I'm using the letter E to represent these vectors, subscripts 1, 2, all the way to n. So there's n of them, and you see how they vary, right? There's a 1 for e sub 1 in the first component, if you will. All the others are 0. For e sub 2, the 1 is in the second place, 0's everywhere else, and all the way down to e sub n, where it's in the last place. Basically, I want you to think in 3 space. Some of you are familiar with the vectors we call I, J, and K. I points in the positive x direction, x-axis direction, J positive y, K positive z. That's essentially the standard basis for 3 space. This just extends it now to n space, so it could be 4 space or higher even. The reason we call these basis vectors is because all the other vectors in n space are expressible as linear combinations of them. So if x is this vector, then we can write it as this linear combination of those basis vectors up there. So if you have the vector in 3 space, some of you write 3, 2, 1, right? Then we can write that as a linear combination, right? 3 times the vector 1, 0, 0. This is the vector some of you call the I vector, right? Plus 2, 0, 1, 0, and plus 1 times 0, 0, 1, of course. So that makes perfect sense, I think. So it's just an extension of that idea to n space in general. Now, so let's talk about functions. What is a function? A function is a rule or assignment that associates each element in one set called the domain with exactly one, right, element of another set called the codomain. Some of you might be saying, I thought that was the range. I remember domain and range for functions. Well, we're going to make a distinction here. Codomain is going to be the other set for us here. Range we'll explain a little bit later. We'll talk maybe about it in just a minute here. But if a function has a domain of A and a codomain of B, we're going to write this notation: the function name, colon, the domain, arrow, the codomain. So domain first, codomain. So we're thinking of mapping. So the function f sort of associates an element A in the domain with an element B in the codomain, and we write this notation, right? which you're familiar with, and we say f of a equals b. We say b is the image of a under the function f of a. B is the value of f at a. So we think about mapping the vectors in the domain to the vectors in the codomain. Okay. So here's a distinction between codomain and range for you. If you think of the basic function here, here's an example of a function that we're familiar with, going from what, this is R is what, one space? This is one space. We usually don't write the one up there. The one space is what? Just the set of real numbers. It's just the set of real numbers. So this is a real valued function. Domain and codomain is the set of all real numbers. And it's just the function f of x equals x squared. So we're familiar with that function. Now, the codomain is the set of real numbers is one space. All the outputs to this function, right, all the images we say under this function reside in the set of real numbers, don't they? So that's the codomain. When we think of range, the range is what the function restricts the outputs to. So for instance, in this case, we know the only outputs to the function x squared will be what? Non-negative values. Only values greater than or equal to 0. So the range for this function f is all real numbers greater than or equal to 0. The codomain is the set of real numbers. So we're going to see that the range is going to be a subset of the codomain. It could be all of the codomain. It could be a subset. A set can be a subset of itself. So that's still true, but in general, that's sort of the distinction. At any rate, I want you to get familiar with the term, so this is probably new, codomain. Here's a function going from 2 space to 1 space, or the set of real numbers. Some of you in Calc 2 have dealt with multivariable, or Calc 3 rather, if you've had it, have dealt with multivariable functions. This is a function of x and y. You plug in an ordered pair, and the output is going to be one real number, right? You just take 2 times x plus 3 times y. And here's a function, domain is n space, codomain again is the set of real numbers, or 1 space. And here's the function's rule. It's basically just a linear combination here. The AIs are some scalars, whatever they are. Then we get a linear combination, but this will be one real number. So you input an ordered n tuple, and the output is one real value function. Okay, so that's pretty easy, but what we want to get to is one level higher than this. Notice in each of these cases the codomain was the set of real numbers, just 1 space. What happens if it's 2 space or higher for the codomain? Well, that's where we get into what we call a transformation. So we call functions of this form, where we're going from n space to m space, a transformation from, again, the domain of n space to the codomain of m space, or we say T maps, as I said, from n space to m space. In the special case, if m and n are equal, if we're going from n space to n space, then sometimes that transformation is called an operator on that space. So here's an example of a matrix transformation. Notice, since we're calling them transformations now, instead of f for function, we're going to use t for transformations. Okay, this is just the name of the transformation. To find this transformation t, this goes from where? 3 space domain, 2 space codomain, and here is the rule here. So you input here into the function t of what? This is the vector x, which is an ordered triple. It resides in 3 space. The output, we'll call that w1 comma w2. Do you see the comma right there? It's kind of hard to see that comma. So it's this comma that, and this is the output, call that w. And so x resides in 3 space. Notice w, ordered pair, resides in 2 space. Okay. Now, this is related now to a system of linear equations because I can say that w1 is what? 2x1 minus 3x2 plus x3, right? So that's that first thing. And w2 is this. w2 is 5x1 minus 4x3, minus 4x3, you kind of understand why I might be writing it this way. Because now I can think of this as being a matrix equation, right? We have this 2 by 1 vector. This is the vector W again. Again, it's 2 by 1. It's vector in 2 space, we say. And then I'm going to write this side as a matrix product. The coefficient matrix is this. So everyone see where I'm getting these coefficients from. Right, directly from this. And times what? This is our, we'll call this A. And this is, of course, 2 by 3. And what are we going to multiply? The 3 by 1 vector, x1, x2, x3. That's the vector x, again, which is 3 by 1. So if I do this multiplication, these numbers again match. The resulting product is 2 by 1. And so this allows us to talk about this transformation up here as just t of x equaling just a x, right? And t of x here I'm calling the vector w. So w is equal to a x. There's sort of two ways, like the f of x notation. If you have f of x equals x squared, sometimes you just say what, y equals x squared. It's kind of the same idea here. Okay. And so you can see why we might call these, as the title of this section was, matrix transformations. Basically, we get the output, if you will, the codomain value, the image of our domain value, by multiplying the domain, the input, by this matrix A. So, real easy. Let's just evaluate, right? What is t of the vector 1, negative 2, 3? Okay. Well, there's two ways to do this. One, I can go up and just use this right here and say it is equal to 2 times x1. And what is x1? Well, this is x1, this is x2, and this is x3. So 2 times x1, which is 1, minus 3x2 plus x3, minus 3x2 is negative 2, plus x3 is 3, comma, 5x1 minus 4x3. x3 is 3. And of course I get what, 2, this will become plus 6, 8 plus 3 is 11, 5 minus 12 is negative 7. Okay, so that's one way I can do it. I can also think of it in terms of the matrix multiplication. So I can think of it the transformation as simply multiplication by the matrix A here. So t of 1, negative 2, 3 is the matrix A. Times the vector 1, negative 2, 3. Of course, I'm going to write it as a column vector. Why? So that the matrix multiplication is indeed defined, right? I've got a 2 by 3 times a 3 by 1, so I get a 2 by 1. And what's the first entry up here in the 2 by 1? In the first row, I take the first row, dot it with this column, so I get 2 times 1 plus negative 3 times negative 2 plus 1 times 3, and then the second row dotted here, 5 times 1, 0 times negative 2, plus negative 4 times 3. And of course, you realize where these are matching up directly with what we have here. And of course, I get the vector 11, negative 7. This is comma or column form, and I can just rewrite that then in comma delimited form, as I did above. It's just typical when we're dealing with transformations. We like to write them this way, especially when you get a real long column. It just takes up a lot of room vertically. But at any rate, it's simple, right? It's just like when you first learned about functions in algebra, and they said, okay, evaluate these functions. That's all we're doing here. So the important key, though, we want you to understand is finding this matrix, and this matrix here, A, has a special name. And so let's talk about that. And again, this 11 comma negative 7, that we say is the image under this transformation of the vector 1, negative 2, 3. So in general, if we have this system of linear equations, we have m equations in n unknowns, x1 through xn are the unknowns in a sense, then we can rewrite it in this form, right, or more briefly, w equals ax. And the system can be interpreted then as a transformation. From where? It's going to be from n space to m space, because we start here, this is the input, what we're multiplying the matrix A by is the input, which is an n by 1, right? And then, of course, we're multiplying by A, which is m by n, and we get the output, which is m by 1. So the input n resides in the domain, right, which is n space, and the output is n by 1 vector resides in m space. And notice this matrix here, the m, the row, number of rows, that's going to correspond to the number of columns in our column vector here. So that m is going to match up with the codomain, if you will, number, the codomain exponent on which space we're in, m space. And the n will, of course, go with the domain. Now, again, we say T is a matrix transformation for obvious reasons. We're multiplying by the matrix A. And T maps the vector x, which is in the domain of n space, into the vector w, which is in the codomain of m space, by simply multiplying the vector x on the left by the matrix A. Again, if m equals n, we say T is a matrix operator on n space. So this matrix A has a name. It's called the standard matrix for the transformation, and it's denoted as either the, if T is our transformation, T in brackets, or if the matrix is A, you might see T sub A in brackets. That's the notation the book uses, so there's the interchange between these, so be familiar with that. So with that talk, let's see if we can answer this question. What is the domain and codomain of the matrix transformation T if the standard matrix for T is this matrix? Well, it has something to do with the number of rows and columns, doesn't it? Right? This matrix is size what? 4 by 6. So remember, I'm going to multiply this on the left. I'm going to multiply the domain vector by this on the left. And so what has to match up? The 6 has to match up. So what I'm going to multiply by is going to be a 6 by 1 vector. Right? And so that's the domain. The domain is what? Not 6, but 6 space. Make sure you understand that's 6 space. We don't write the number 6. The domain is not 6. That's a number. 6 space is the set of all 6 tuples. And codomain, then the output of this, right, what are we going to get? Well, a 4 by 6 times a 6 by 1 gives me a 4 by 1, right? 4 by 1. And so this is going to be 4 space. Okay, so again, this number of columns for our standard matrix corresponds essentially to the domain, if you will, of the transformation, and the number of rows will correspond to the codomain. So that's important to remember. Here are two simple a transformation and an operator, very basic. If the standard matrix is the zero matrix, we'll use capital T with a subscript 0 for that transformation. What's going to happen when I multiply by 0 matrix? Every output will be the 0 vector. Okay, so this particular transformation is just called the 0 transformation, and for every x in the domain of n space, the output is the 0 vector. By the way, just some notation here. I'm not sure if you're familiar with this little symbol here. This little symbol means is an element of, or is a member of, or is in. So x is a n tuple is what this is saying. X is in n space, so it is an n tuple. T with subscript I is going to be what we call the identity operator. Of course, that is where the standard matrix for that transformation is the n by n identity matrix. And of course, it's an operator because the domain and codomain are the same. It's a square matrix. And of course, this identity operator, whatever the input is, x, that's the corresponding output, because when I multiply by the identity matrix, I of course get the actual vector back. Okay. Not all transformations are matrix transformations. So for example, the transformation going from 3 space to 2 space defined here is not a matrix transformation. There's no matrix A where I can write, W here is equal to A times X, right? X being an ordered triple in the domain, output being a ordered pair in the codomain. So there's no matrix A that will work that. And you can probably see here why. This is not a linear system of linear equations here, is it? Right? Because I'm squaring, I'm multiplying here, so that's not a situation. It's still a transformation. I mean, I can still plug and get outputs to different inputs, right, by this relationship, but it is not a matrix transformation. Now, the following theorem gives requirements for a transformation to be a matrix transformation. So if you have a transformation from n space to m space, it's going to be a matrix transformation if and only if these two properties hold. And basically this says the image of a sum of vectors in the domain is the sum of their images in the codomain. And the image of a scalar multiple in the domain is that same scalar multiple of the image in the codomain. These are called the linearity conditions, and such transformations that satisfy these are called a linear transformation. So we're going to deal specifically with matrix transformations, and matrix transformations are linear transformations. Sometimes we'll interchange and use both phrases, matrix transformation, linear transformation. If we make repeated use of these rules for any linear transformation, then if I take the image of a linear combination of vectors in the domain, then that's going to output as a linear combination of the images in the codomain, where the coefficients are all the same, the k1s, these scalars, k2, and so on. And so this gives a actual theorem that allows us to test. So for instance, if I went up here, this transformation here does not satisfy both of these conditions. All right, one last thing to look at here. And I brought this out because this is going to be helpful here. If X is an ordered pair, then I can write that as x1 times e1. If you remember e1, that's that vector 1 comma 0, the I vector like you're used to hearing, right? And e2 is the j vector, if you want to think about it that way. I'm going to define the look at the transformation from 2 space to m space. Okay. Then t of x is going to be t of what? Well, x we said is equal to this linear combination x1 e1. Notice the difference between x1 and e1. x1 is a scalar, e1 is a vector. x1 and x2 are real numbers, e1, e2 are ordered pairs. Okay. Well, if t is a linear transformation, if t is a matrix transformation, then by this property here, I can write this as x1, that's the scalar, that's the real number, times the image of e1 under this transformation, plus x2 times the image under this transformation. Again, if t is a matrix, we'll just say transformation. Okay. Now, what do we know about these guys? t sub e1. What size vector is this? Well, the domain is 2 space, but what's the codomain? M space. So this has to be an m by 1, right? The image of e1 is going to be an m by 1 vector. And so this is a scalar, this is a vector. Same with this, m by 1. Okay. But this is a linear combination of two column vectors. If you remember, I can think of that as a matrix multiplication where these columns can form these column vectors can form the columns of a matrix. So I'm going to put this column and I'm going to join on this column together, right, times our 2 by 1 vector x. And this right here is going to be what size? This is going to be, right, m long, right, because these are m by 1, but it's m by 1, m by 1, so a total of what? M by 2. There's two columns. And so when I multiply, notice the numbers are the same here, 2 and 2, and I get m by 1, right? And this right here, this is the standard matrix, right? Standard matrix for the transformation. And so what we have shown here is an example of the following fact. If you want to, another way to find the standard matrix for a matrix transformation is you simply find the image of the standard basis under the transformation, and you put those into the columns. Here we only have two columns because, again, the domain is 2 space. If the domain is 3 space, we're going to have 3 columns, right, where we'll take the image of E1, E2, and then E3, you know, I, J, and K, and so on. Okay, so I just want to close with illustrating that particular type of situation with this example here. Let's find the standard matrix by this process. This will give us 2 ways to find the standard matrix. We've already shown one way. So here the domain is 2 space, so I'm going to look at the image of the vector E1, or I if you want to call it that, right, 1, 0. What's that going to be? Well, I can plug it in and see here, x1 is 1, x2 is 0. So I'm going to get 3 times 1 minus 0, comma, x1 is 1 plus 5 times x2, which is 0, comma, negative 2 times 1 plus 0. And of course I'm going to get 3, 1, negative 2. Okay. Well, I'm going to take that 3, 1, negative 2, and I'm going to slide that in to the column 3, 1, negative 2. Slide that 3, 1, negative 2 into the first column, and this will be the first column of my standard matrix. Okay. What's the second column going to be? The image of the E sub 2. Right, since 2 space, we're just looking at those two. And so this is T of 0, 1. And if I do that, now x of 1 is 0. So I'm going to get 3 times 0 minus 1, 0 plus 5 times 1, and negative 2 times 0 plus 1, which gives me negative 1, 5, 1. And that is going to become the second column down here. And there is my standard matrix. This is the standard matrix for T. And that's the way we denote it. Again, you could have done this also by writing out the system of linear equations and getting the coefficient matrix, and I'll have you check that out and make sure you get the same standard matrix that I have here. But it's just another way of finding a standard matrix for a transformation. So basically that's it for matrix transformations. I want you to understand how to find images, obviously just plug and chug, if you will, under the matrix transformations, how to find the standard matrix for the matrix transformation as well, and to know the domain and the codomain, is which is which. Okay, so the homework will illustrate that pretty easy stuff, and hopefully we'll come back to this a little bit later in the course as well, and elaborate a little more on it.